I just use
Hi. So my name's Robert. I'm a staff developer here at TextNow. I work sort of shaping the core experience for our services, and I'm going to be giving a talk about the gRPC piece and the build system Bazel that we've been bringing into our Go infrastructure. So as we've kind of talked about a little bit already, our backend stack at TextNow is predominantly now a series of microservices that are built using Go. This pairs quite nicely with the gRPC infrastructure. It makes it very easy to create new network services that we can scale independently. As Ian talked about, we use the monorepo for all of our Go microservices. This makes it easy to spin up these microservices, and it gives us the advantage of taking this common set of build and release tools, like our linters, formatters, build rules, and only needing to write them once. Early on, we decided that we wanted to use the gRPC framework to sort of define our inter-service communication mesh. It makes it very easy for us to write clear contracts that services need to abide by on both sides, and it really helped improve the level of documentation for our internal microservices. One of the struggles we had when we were writing like Ruby microservices is that in Ruby, you have this sort of like convention around how REST API is supposed to be built based on the code that you've written, and that doesn't really translate well into auto-generated documentation or things for people to read. You have to go into the actual Ruby files and see what you've got. And we kind of learned that that was hard to work with, and decided that being more explicit about what these contracts needed to be would just make the development process much easier. So I'm going to be talking about our evolution of gRPC and where we're up to date, and a few things that we're looking at over the next 3 to 6 months. So we began adopting gRPC Go about 2 years ago. Over the last 2 years, we've added about 3,000 commits to our monorepo. There's 34 contributors. This includes co-ops, full-times, and people from a number of teams other than just the backend team. We have about 3 dozen microservice daemons, about 2 dozen CLI tools, and a half dozen lambdas, a few others sort of like miscellaneous things that run in a bunch of other compute environments other than just Docker containers. And we've obviously learned a lot along the way. The version 1.0, I'm going to kind of bucket what we've done into 2 major different versions, because we went through one version, learned a lot of things, and then decided to redo it all, and got to version 2. And version 2 will have a lot more detail as to why we made some of those choices. But version 1 started with a first commit, as I guess all repos do. And it basically had a very small gRPC API that was defined in a proto file. It had a daemon that implemented this contract, and then it had a very small CLI tool that exercised that daemon's contract. The logic of the daemon wasn't significant. You can think of it as like an echo process that took in some data, did some translation, and returned a result. Simple unary request response. But it gave us this playground to try a bunch of things. What project structure did we want? What build tools were we going to use? And how we're going to generate the code out of the proto that we defined. We first sort of settled on this idea of separating the proto definition from the actual code that implemented it. So we had proto as a top-level directory where we put all of our proto files, and this was exclusively domain of our services. Our service definitions. And then we had a second top-level directory that we just called services, originally enough, that was a collection of all the services that we had written. And here within each service directory, we had a subdirectory that we called PB. And it was the location of all of the auto-generated code that that service was going to depend on. The service itself also had like an API.go where the code to actually satisfy the server API of that interface was defined. There would be some other .go files that had business logic related to the responsibility of the service. And then we would have a CMD directory that was broken into 2. One service named D, which was the daemon process that would actually listen and respond to network requests. And then it would be service CLI. And the convention we had was that for every daemon service we were going to write, we were also going to have a CLI tool that would let the developer test that particular service. Because at the time, the gRPC curl and the other tooling that's kind of formed around that space didn't really exist. You didn't have a Postman equivalent. People wanted a way to test that particular service implementation. And so we just asked developers to write very basic CLI tools that would perform the request that the service was processing and then display the response. we, as I mentioned, had all of our proto files in one directory. Each file would define its own namespace, and we would have common types that would be shared across multiple proto files. To define how the auto-generated code in the Go space would be structured, we use the Go package directive, which is one of the pre-compiler options that you can use to control how the Proto-C compiler outputs the gRPC code that you are going to use. And this gave us control over how the protos themselves got mapped into particular services. And we had a directory called PB that we created more from a convention perspective to make it easy to distinguish what was auto-generated from what was actually written by the user, so that we could have the same type potentially include ORM-specific fields for services that were accessing a database, conform to other interfaces that the dependent services of that service were calling out to. And this just made it very clear what was a proto definition and what wasn't. The process of doing the build required us to automatically move the auto-generated protocode out of the build directory and into the right package in the file system directory manually, and that was not fun. So our build script was, as all good build scripts start out as, a shell file that called a compiler and put some stuff into a directory called build. This basically took whatever service we were building, created the output from Proto-C, made sure the right proto options were being specified, so making sure we were always using the gRPC plugin, making sure we were using the right output path, and then it just put these pb.go files on in the file system on basically a directory that was ignored in our git ignore, and then we would copy it out of that directory into the particular place on the path, and then we would run go build or go run to get the code going.
That sounds painful.
Yeah, as it turns out, there's a few lessons learned, and that third one is that manual steps are always forgotten. So there was more than one time that we would end up committing a change to the proto file and not have an auto-generated result that would match it, and so we would deploy services assuming the contract was X, but it was actually Y. This is a bad idea. Bad results come out of it. Putting all of the proto files into a single directory wasn't a great idea. The original intent was that by keeping all of our service definitions together, it'd be very easy to identify common types, avoid people re-implementing the same concept on a package-by-package basis. But after we got to a full directory of proto files, it turns out people don't click into each one of them to see what type exists. And so that benefit didn't really get us what we wanted. And furthermore, when you have a single directory with all of your protos, it's very difficult to distinguish what you want to be a public API that your clients should consume and what is an internal API that you can easily version. So when we talked and thought about field version deprecation, it's a lot easier when you're within your internal infrastructure to say, in this version, this field is optional. In this version, this field is deprecated. And in this version, don't write this anymore. You can enforce that. You can't do that on a public API. And there was a few times where people would read one API, think it was private. It would turn out it was public. And then there was just some problems managing how our APIs were being exposed. So that didn't work the way we hoped. And then I think the bigger thing that we learned was that keeping types that are auto-generated in separate packages than the services that are using them adds a lot of unnecessary complexity. So this caused a couple of problems. One was that we'd end up with the same type having different names, and people would import the wrong one, assuming that they were getting the first one. So you would take the like user as a simple model, and you would have a manually written user file that would have an ORM mapping that lets you persist to the database, and then you would have a proto-generated user object that would have the correct serialization to go over the wire. You would import user and then try and save it to the database, and then it would be like, I'm not an ORM thing. Why are you trying to do this? And you're like, well, because so then you would correct your import, and then you would just do this all the time, and it was not fun. And then kind of out of that, we learned, well, we knew, and we kind of explicitly chose not to let people extend the prototypes because we didn't want to run into situations where we changed the underlying definition and got into trouble. But then there was a few cases where like this would be super handy. So the times where it was super handy to extend auto-generated types made it really frustrating when we couldn't do that. So we kind of decided to take a step back. We lived with version 1 for I'd say about 6 months. It started with 1, and by the time we sort of finished up, I'd say we were maybe at a dozen services that had maybe a dozen developers on them. It was a fairly small subset of where we are today. And we kind of laid out a few ideas as to what we wanted to do differently and what we learned from V1. And one is that ease of development is important. If it's not easy for a developer, they're probably not going to do it. We wanted to support this idea of multiple build targets. So in V1, anything we could do, but we had to do it manually. We wanted to make sure we could easily build binary results. We could make Docker images. Our build system would make it very easy for us to generate the assets that we would want to deploy. We wanted to automatically support gRPC build targets so that users didn't have to do anything on the Proto-C side. As we started scaling our monorepo, build times started getting worse and worse when you were doing it all manually. And so we wanted to make sure we could get a solution that would give us some better build times. And then the final result is that we wanted the build process to be consistent across platforms. So if developers were on Linux, if they're on Mac, we tend to use Macs for development and then deploy to Linux. We wanted to make sure that the output was going to be the same and that the build process didn't have specialities for one or the other. So we kind of did a survey. We kind of came to two, I think, fairly popular choices around building Go code. The first was Makefiles, and the second was a tool at the time called Bazel. Still called Bazel, actually. And I mean, Makefiles, they're tried and true. They're easy to get started with. But as you build up a directory of them and you add a lot of dependencies, it can get pretty complicated to manage. CMake is a project. It was existing only because Makefiles are hard to manage at scale, and it became its own language, and I didn't really want to go down that path. Furthermore, remote caching is something that is not really offered by Makefiles. Like, you can get like compiler level caching that comes out of what Makefiles generate, but you don't get the framework doesn't provide it yourself. When we looked at Bazel, we saw a lot of things that we liked. It gives you fast parallel builds with remote caching and controllable build targets. It supported gRPC natively. It had a lot of supported languages, but it was definitely bleeding edge. 18 months ago, it was going through heavy development, and the documentation basically didn't exist. So if we wanted to do something, we had to read the Skylark source code and figure out what the hell to do, and then do it ourselves. So it was something that was definitely going to get us where we wanted to go, and we kind of banked on this fact that Google was going to continue developing it, and we decided to go with Bazel. We chose it, and specifically we chose the rules_go subsection of Bazel. Bazel is a generic build executor, and then it has a series of rules that control the compilation and the generation of each of the different programming languages that the framework enables. So rules_go is the part of Bazel that you want to use if you're going to be building Go code using Bazel. It has both native support for Proto and gRPC build targets, which is super handy, and it uses this tool that's called Bazel. And Bazel is effectively a Bazel build file generator that looks through your file system, your package hierarchy, looks at the dependencies, and then generates everything for you automatically. So the idea is that every time you make a change, you rerun Bazel, your build system is all up to date, and you can build it. And when things don't change, you don't have to rebuild them because it's kept a status of everything that's already built, and it just avoids rebuilding those things. It's able to both analyze Go and Proto files so that we don't have to manually write any of our Proto library declarations either. And we basically allow it to automatically handle our vendor references. So we have today a directory called vendor that contains all of our checked dependencies through GoDep. We haven't cut this over to Go modules yet, but the Bazel tool supports both. You can either have your vendor dependencies where it basically generates build files for everything below the vendor directory and handles the package rewriting to ignore the fact that it has vendor in the name. And it also supports the Go module process where it actually generates native Bazel dependencies in the workspace file based off your Go mod file, so that you don't have to check in any of your vendor dependencies. It just calculates the SHAs and all the dependencies of the modules that you pointed to. So if you already have them downloaded, it just takes what's local and goes with it. So in an ideal world, adopting Bazel is pretty straightforward. You brew install Bazel, or you, whatever your Linux package manager is, install Bazel. You take the default workspace and build.bazel files from the rules.go git repo and set them up at the root of your project. You run bazel run //:Bazel, and you do bazel build //:. So it takes a similar syntax to Go in that it uses ... to mean here and everything below me. And Bazel is a sort of a synthetic build target that invokes the Bazel tool to run on your repo. Now, if you have a brand new project, this will probably succeed. you'll have all of your automatic generated dependencies, and you'll be able to look at the build output, and there'll be assets that you can consume. If you have an existing project that has a structure that it is happy with, then you're probably good to go. Chances are you may have a few things that it's not going to be happy with, and you'll have to make some tweaks. In our case, it definitely did not work. It was a learning opportunity. And there was a few things that broke. One, and this one was early on, Bazel does not like multiple proto packages in the same directory. And this is because it doesn't generate its build targets out of path, and so it basically tries to take everything and create a single proto library target in that directory. It doesn't like compiling 15, 20, 30 different proto files that are all actually different build targets at the same directory level, which means we needed to basically manually write the build targets for our entire proto structure and say Bazel ignore proto. That was painful. We had also checked in a number of our auto-generated targets, which Bazel happily generated its own build targets for. And of course, we now had duplicate references everywhere. So this all basically came down to how we thought about our proto structure. And by readdressing that, we were able to solve basically all of the issues we had with Bazel, and in particular Bazel. So we basically decided to change our thinking and split protos into one of two concepts. One is either an internal proto that is managed only for services and should not be exposed to our clients, and the other is a public proto that we declare in a separate hierarchy. So for our internal gRPC service protos, we moved them into the package that is actually going to be implementing either basically implementing the server interface. We got rid of this idea of a PB package, and now we use the type where it lives. This gives us the ability to extend them, and if there's any cases where we do end up deciding to have a parallel type that is handwritten, be it for persistence through an ORM or something like that, we put it in a sub-package and hide it behind an interface that uses that auto-generated type as the contract. So it becomes the implementation of that interface's responsibility to manage its type. It's not the generic type that that service owns and manages. It also actually made it a lot easier to test some of our dependencies by putting the contract in place. We didn't have to worry about ORM types passing the package boundary. For public gRPC services, we've kept the idea of a separate directory hierarchy, but we use it to basically match up to the API that we're exposing. So we actually learned after the fact that we conform very similarly to the Google Cloud API recommendation for package definition, where you have the service and then you have like a V1, V2, V3, V4, whatever, and then the service implementation proto underneath each of that version directories. And this makes it very easy for us to, given a single service, implement multiple versions of the same API, because when we actually go in the daemon to register the listener, we basically say, take API and register it for V1 of this public interface, register it as V2 of this public interface. And as long as it has methods that support all of the operations that API needs to support, all of that code still lives within the same service, and it becomes very easy to manage versions and deprecate public versions. So as an example of our internal API structure, we don't have anything outside of the services directory. We have the service name. We have API.go, which is still the file that has the implementation of the public service contract. We have the service contract defined in testservice.proto. We may have some other Go files that have the business logic required, and then we still have test service D and test service CLI with the same daemon and CLI pieces to it. We use the service CLI piece much less now that tools like gRPC curl are options, but for older projects that we still haven't written for, there may be some custom things that we've kept in them, and so we do have them just sort of by convention. For a public API, the service structure is very similar, except we don't put any of the proto files in package. We keep all of the services outside of the API, service name, version, and then service proto file. So we can have V1, V2, V3, V4, see them all separately, and it becomes very easy to understand what does V1 offer, what does V2 offer, what does V3 offer, what does V4 offer, and then at the top level test, you can say what is version 1 versus version 2, just in a readme.md file, and it's very easy for people to read and understand what the differences are and why they should be on version X versus version Y. So at this point, we use Bazel to generate Go build targets for all of our proto-defined objects. We have, obviously, in the build target, both the client and the service does get generated. That's just what comes by default. And then Bazel auto-links these into the build targets for the services that depend on them automatically. We manually add in build targets for our Dockerized services. So once we've run Bazel and it's created the Go binary, what we will do is include the rules Docker rule set, and then we'll use the Go image. We've actually sort of customized Go image to be our own Go container rule that contains the actual binary embedded in a Docker container and lets us run it from scratch. And then we've also started manually adding, experimenting with adding build targets for public APIs on other languages. So by default, Bazel supports things like Java, C++, PHP, and as long as you import rule sets that let you define the build targets for those languages, it becomes very easy to output not just Go code that conforms to the gRPC API, but you can also output PHP code, Ruby code, Java code, C++ code, etc. So what I went and created was a little GitHub repo that has this example project structure in place. You guys can clone it and use it and learn from all of the things that we've learned. But it has a public gRPC service with a public gRPC API with an internal service implemented. There's a Dockerized daemon and a CLI tool to exercise it, and it's all built with Bazel. So you just do Bazel, you'll install Bazel and then go into the directory and you can do Bazel build / and it'll get you all your targets and you can run them if you want to. So at the end of version 2, things are a lot better than they were, but they're still not perfect. And these not perfect things fit into a few different categories. One is that the advantage of Bazel is that it auto-generates all of your dependencies. But within its build structure, it has its own out-of-path build structure that it keeps all of its assets in, which means that your IDE can't reference the auto-generated pb.go file that your target has auto-generated for you. So you still need to copy that asset out of the auto-generated path and into your own file system for tools like Golang to autocomplete all of the types. This is not fun. There is an open PR against rules Go to use a new intermediate target that Golang is supposed to be able to target, but they put a pin in that till Bazel 1 comes out, so it's still in progress. This is more a statement of a monorepo, but when you get more and more build targets, you definitely need to set up build caching at some point. It will get very slow to do a clone and a rebuild of everything, and as your build systems start to run these more and more frequently, you want to make sure that you have nice caching set up so that you don't have to spend time pulling down the Go code, the Go source code and compiling it, the gRPC source code and compiling it, the Proto-C source code and compiling it, and all of these dependencies of it. That will obviously just take time to build. Building for Docker on Mac is sort of an awkward thing outside of all the discussions about Bazel in particular. We need to add some custom scripts to manage the building of services that are going to run on OS X versus services that are going to run in a Docker container on OS X, because the binary that gets embedded is built with the platform instruction set. It's not built with the target instruction set. So if you build a container on Mac through Bazel, it'll by default include the basically the OS X instruction set into the Linux container, and it just doesn't work. So you need to supply the platform argument to say, hey, these targets are actually supposed to be built with the Linux cross compiler. Please embed that result into the Docker container. Otherwise, you're going to get basically instruction issues where it doesn't work. And I mean, that all being said, V2 is a lot easier to work with than V1. Looking forward, there's a few extensions to gRPC in particular that we're exploring today. And the first one is API field validation. So gRPC is great. It gives you typing. It tells you what all of the types of your contracts are supposed to be. It doesn't let you get into the specifics of how do you know if a field value for that particular type is going to be accepted or rejected. And defining that in a platform consistent way can be tricky. So what we've started exploring is this idea of having basically field validation built into the proto so that consumers can just immediately see this is supposed to be an IP address and an IP address is this. And it doesn't matter what service implements it, as long as it matches that particular field format, then everything will succeed. At the moment, there's sort of two major projects that are competing against each other in the space for Go in particular. One is called Go Proto Validators, which, as its name suggests, is a Go validator library that Proto compiles. And it generates code in Go, and it automatically adds to your proto-defined type a method that's called .validate. that returns a bool and an error. And if you build this target, it will automatically include another like pb.validator.go file. You copy it all into your build directory, everything works just fine. And then as long as you make sure you call .validate before you use the type that's passed into the API, you're golden. There is a build type for this built into Bazel. Unfortunately, it only includes the Go library dependency definition. It does not include the higher level proto library definition that you need to import if you want to properly generate your proto definitions. And this is okay if you've checked in your vendor directory and you have all of those things in place. You can do some Bulldozer magic. Bulldozer is a tool that lets you rewrite Bazel files underneath the system to basically say this is what the target's supposed to be. When you're going to Go modules where that's all defined at your workspace level and you don't actually have the source code, it's a lot more difficult to get that build target working properly. And when I say a lot more difficult, I wasted a day and said I'm not doing this anymore, which led to the sort of competitor, which is a project that's sort of sponsored by Envoy, which is a service mesh framework that's part of the Istio larger scale project. And they have their own Proto-C validation generator. The difference between this and the first one is that it actually generates code across languages. So you get validators for Go, Java, and Python. By default, there's an active project on C++ to also provide a .validate method in C++. And it today has native support for Bazel. So it has Bazel targets for all of the validator logic from a proto perspective and a Go perspective. And as long as you do a little bit of a hacky import of it into your top level build.bazel file, everything works underneath, which is super handy. That this particular piece is in that demo repo that I pointed out. Next sort of thing we're looking at is this idea of linting. We lint our code. Why shouldn't we lint our APIs? The idea here is just to, again, identify style issues, consistency, and make sure best practices are followed. At the moment, there's two popular ones that I found. One by Uber called ProTool, which is actually more than just a linter. It's like a full proto build tool. With all of the infrastructure we put in place, we're probably going to only use it as a linter. But it lets you basically pick and choose the style guide you want. You can use Uber's v1, Uber's v2, or Google's style guides, and it will basically tell you if you've missed any field naming, typing, conventions, things like that. The other is a project actually that's offered by the Google APIs team, which is sort of the group that is building all of the Google Cloud APIs for public consumption. And they have their own project called API Linter that somewhat unsurprisingly enforces the Google style guide. So if your APIs conform to the Google style guide, cool. It's a pretty simple API linter. Both work, and I haven't found a good reason to use one versus the other at this point, but they're both fun to run against your APIs to see what you've messed up in the past. Sort of looking past the short term, the next thing I think we see as being the direction of where we'd like to go is instead of just auto-generating code to communicate with our API, we'd like to be able to abstract it one level further and build a full level client SDK. And the big distinction here is that instead of just saying, how do you serialize data, how do you pass data over HTTP2, we're talking, how do we handle retries? How do we handle backoffs? And codifying this behavior is something that is just manually done today. We go to the client team and say, this route behaves this way, this route behaves this way. If you get this error code, don't retry. If you get this error code, please retry. Please use an exponential backup here. You can retry more aggressively here. And it's basically a lot of work to do this manually. The Google Cloud Project team has released a project that they call the gRPC generator, which takes a YAML file that codifies all of these rules, and it outputs an SDK that uses the gRPC definition plus the service behavior that you've defined in your YAML file to be something that you can just call directly. And so this is something that is basically targeted to Google's infrastructure. So it supports Java and C++ and Python today, and it doesn't support the more modern Swift, Kotlin mobile targets, unfortunately. But it's something just to put on people's radar. If this is a problem you run into, there's a potential path forward, and I do plan on keeping an active eye on this particular.
They plan to add Kotlin support because Kotlin's a first-party language on Android, right?
Yeah, it is for one part of Google, not this part of Google yet. So Kotlin and Swift and gRPC are still. This is actually something we're working through right now, where it was. You can generate Objective-C and Java code and it looks perfect. But then you pass it to a mobile team that's like, we only write like Kotlin, we only write Swift. It's a little bit harder to then say, well, this is how you would integrate this, like this style of code that you don't really want to write anymore to a newer framework. They do both have projects that the Google APIs team is working on, but they're not a first-class citizen with the Google APIs team quite yet. So it's definitely something that I have my fingers crossed will improve over the next like 3 to 6 months. But at the moment, there's still a little bit of friction between going right to Kotlin or Swift. That is my last slide. So I will open things up to questions.
How do you deploy your services in general? I asked because we went through a process of putting up gRPC stuff, and we came across some very funny behavior with load balancers.
Yep. So, what's that?
Sticky sessions?
No.
Yeah. So we deploy our services sort of in two contexts. We deploy some services in AWS into a Kubernetes environment, and we deploy other services in Docker containers on hosted hardware, where we have load balancers that we manage ourselves and do basically like pooling around. What we've done is crank down the connection timeouts and the connection lifespans, so that when a service basically wants to be removed, we kill it, and then the sessions just reconnect to another thing and then do the deploy. It's not super graceful, but the improved load balancing is on the list of nice to haves, especially because it's like a framework. Load balancing is left to the implementer to solve. We did explore the idea of like doing an internal service mesh based on Envoy, having everything point to localhost and then have the mesh manage that. And ultimately, it's like a project that we'd love to find time to get going, but it's not something much more graceful than that today.
Okay.
We also looked at client-side load balancing because gRPC does support that. But in our hosted environment, we do not have good service discovery. So we have it on the Kubernetes side, but we don't have it on our current Tolo. And that is an absolute requirement for any client-based load balancing, because you need to know how many services are up and where they are. And you need to be able to just ask that. So it's the experiments were looking reasonable, but without it, just didn't have time to deploy our full blown when we were looking at AWS and Google. So.
Well, word of warning, don't use AWS's network load balancer, because it will look like it works until you have both your client and your server on the same machine, and then it doesn't work. Hairpinning is apparently not supported. So we ended up solving that by using the client load balancing.
It's good to know.
Don't do that.
Is there a reason you guys chose gRPC for the client side, like from the public? I'm assuming, like, forgive my ignorance about what TextNow actually does.
We're calling a messaging app that lets people.
Right, so you have an app,
like,
and it talks gRPC to, like, via a public API to...
Today it talks HTTP to the public API,
Right.
and we have HTTP gateways that then convert into gRPC. We want to be using it on the client side, but there's a number of things around networking.
So my question is, why not HTTP on the client side?
So I think the reasons fit into one of two buckets. The first bucket is just consistency around deployment. So the idea of defining like a service in one language and then letting all the client teams just pull it, link against it, and then go has a certain level of appeal. I know you can do that through like OpenAPI, but you then have your proto to OpenAPI compile step, which then you need to compile to all of your client libraries. It's doable. It's just like another like step along the way that we were hoping we could avoid. The other sort of fits into, there's certain streaming use cases where gRPC's like bidirectional streaming semantics are very advantageous. And if we're going to go that path over like a WebSocket channel or an HTTP2 socket, you may as well get the framework that gives you that over that socket anyways, instead of trying to rewrite it yourself.
So it's partially due to that you're sharing like entities between your private APIs and your public APIs then?
Yeah.
Okay, that makes sense to me.
So how do you guys mark any of the protobuf definitions somewhere, or how do you?
No, so we basically use the protobuf as like the concrete type, and it's what gets passed between interfaces. So if we build mocks on the
Sorry, I meant to ask, gRPC calls, do you mark those?
gRPC call, like outbound calls.
Right.
Yeah. So there's a project that lets you basically set up an in-memory gRPC server, and it just like does a loopback, so you can do it that way. Yeah, I'm trying to think.
Generally, the service will have an interface, and if we need to implement that interface, we can just mock like the interface inside of it. So we just have to implement any of those methods. We can make it do whatever it wants to do without actually getting to where we're still at native encoding. We haven't actually transcoded them to network encoding. We just at the native level intercept, do whatever we feel like.
So you bootstrap that piece of code manually, or is there some auto generation tools that you use to get that?
I personally use a VS Code plugin that just lets me point at any interface and generate a bunch of client code. Other people on the teams that do different things.
I write stuff by hand. I'm a sucker.
You guys run into any coupling issues sharing entities like that though? So
We do keep them like decoupled to a certain extent. So having like the V1, V2, V3, we do some translation from older versions into the internal type.
so you have a policy around some process around backwards incompatible changes, right? Like I want to change the user entity in an incompatible way. There's a process for me to introduce a new user entity or
Exactly. Yeah. We do like you can make minor changes to the API, like basically field extensions is all we really allow. And if you want to like remove something or make a substantial like semantic change, then bump the public API and then work with the client teams to make sure that they take advantage of that.
And I'm even including like the private APIs on that, right? So you have multiple services that might care about what a user is, right? So service A needs an update, so they want to update what a user is, and like service B is like, oh, it's working, so you can fix it.
We went through this on like we have multiple like pipelines where service like microservices kind of go like A to B to C to D, and they're doing transformations along the way. We had to do like a major bump of a type, and what we ended up doing was just running parallel versions of the API, like A and B, and passing over A or B based on how we'd gone, and we just made it like a team initiative to migrate from A to B along the way. And so it took a little bit more time than I think we wanted, but we learned a lot from that exercise, and in general, it worked really well. Just need to make sure you commit to when you start it, push it all the way through.
And most of the time, it was just like shim code that on the old route that immediately like just did a little bit of munching and put it to the new route. So it wasn't like that. Well, this is actually did most of the work, so you know how much effort it was.
Don't do it over Christmas break.
Freeze the code for 2 weeks before Christmas.
Lessons learned.
And then one other minor note, just because you mentioned Envoy, there is actually, as I believe, a feature of Envoy, a HTTP to gRPC translation layer. So it's capable of rewriting HTTP requests into a gRPC model and then translating them back in transparently to clients.
Yeah. We looked at a couple different options. What we've gone with in the short term is we take that library that it uses. It's actually a Go project itself.
Yeah.
And we embed that as a dependency within some of our public microservices. And we run both the gRPC and the HTTP endpoints within the same service. And we basically write. So the fun part about the gRPC gateway project is that you can't pass in, or you can't register a type that conforms to the server interface, because the gRPC gateway depends on the client interface, which is the exact same, except it has the gRPC dial options as the last thing. So we have this really small process whereby we write what's a shim, effectively, that takes the type and just calls them out directly and ignores the gRPC dial options. It works pretty well. It's a little bit of manual code, but by and large, it's avoided us needing to deploy another service in, again, a hosted environment. I think running in both like AWS and on bare metal makes some of those things that are very easy to do in Kube a lot. It's not that it's hard, it's just it's a lot of work to then add another like piece of underlying infrastructure to your stack.
Yeah.
And the SRE team's like, oh, do you really want to bring up another service, or you sure you don't want to do it yourself? And sometimes it's easier just to like embed it into the service and you go from there. Cool. Thanks, everyone.
anyone need a quick washroom break before we move to the next talk? If so, maybe we can like take 5 minutes tops. 5 minutes.